Hello, sir. My name is Pishreya. I'm from EC branch B section, and my tech talk topic is Fundamentals of Audio Class D Amplifier Design, a review of the schemes and architectures. Introduction. So Class D amplifiers or switching amplifiers are popular components in mixed signal IC design and widely adopted for smartphones and tablets with rich multimedia thanks to the high efficiency and high output power capability. Their applications range from audio and video drivers to an envelope tracking for power amplifiers. So audio amplifier classes. Class A amplifiers are the most common type of amplifier class due to their simple design. A class A literally means the best class of amplifier because of their low signal distortion levels and are probably the best sounding of all the amplifier classes. The Class A amplifier output stage is never driven fully into its cutoff or saturation regions. Then the transistor never turns off, which one of its main disadvantages and implies that the efficiency is very low. Class B amplifiers were invented as a solution to the efficiency and heating problems associated with the Class A amplifier. The basic Class B amplifier uses two complementary transistors, either bipolar or field effect transistor FET for each of the waveform with its output stage configured in a push-pull type arrangement so that each device amplifies only half of the output waveform. We can create a structure called as class B, which offers both a high linearity and high efficiency. As its name suggests, the class B amplifier. A drawback of the CMOS class B output stage is the limited output swing range due to the headroom requirements for certain audio output levels. The higher the audio supply, the lower the efficiency. Typical audio or music has 10 to 20 decibels factor. Crest factor is definition of the ratio of peak amplitude to the root mean square RMS value level. The class G topology uses multiple power supply rails of various voltages and automatically switches between these supply rails as the input signal changes. Its constant switching reduces the average power consumption. Here we can see the figures of Class A amplifier, Class B amplifier, and a CMOS Class AB audio amplifier, and the Class D amplifier and Class H amplifier, which has a amplifier and a signal detector and efficient two-level supply modulator. Class D amplifier. The fundamental limitation for a linear amplifier is that the transistors inside a linear amplifier operates in the saturation or linear region. There is a relatively large voltage drop when a large current passes through the transistors, resulting in a large power loss that inevitably hurts efficiency. Ideally, we want to make output devices into the switching where the current and voltage are out of phase. Specifically, when a large current passes as output switch, the voltage drop across the switch is zero. Switch on, or when the large output drops a switch, the current passed through the switch is zero, switch off. This implies there is zero power loss in the output stage. This is basically the principle of Class D operation. Class D operation, as shown in the figure 6, the first modulate the audio signal in digital or analog format into pulse width modulated signals, and these signals then drive the output switches. The output pulse width modulated signals are then filtered by either external filter or by the speak coil itself. Class D amplifiers theoretically can reach 100% efficiency. Figure 6 shows the Class D amplifier, and figure 7 shows that the efficiency comparison. Class D modulation scheme. The most common Class D modulation schemes are pulse density modulation (PDM) or pulse width modulation (PWM). PDM is a form of modulation used to represent an analog signal with a binary signal, and its output is a stream of single bits representing a sample signal. In a PDM signal, specific amplitude values correspond to the relative density. The output of a 1D digital to uh, analog converter DAC is the same as the PDM encoding of the signal. Figure 8 shows the PDM waveforms where the green curve is the input analog sine wave and the blue curve represents the corresponding PDM output waveform. Here we can see the wave of the PDM and PWM. PWM is a special case of PDM where the switching frequency is fixed. For a 50% voltage with a resolution of 8B, a PWM waveform will turn on the 280 128 clock cycles and then off the remaining 128 cycles. With PDM and the same clock rate, the signal would alternate between on and off every other cycle. The average is 50% for the both waveforms, and the PDM signal switches more often. For the 100% or 0% levels, they are the same. The zero crossing of the input level, the analog input signal drifts slowly from positive to negative. In this region, PDM modulator output toggles at the range at the average rate slightly lower than Fs by 2, and for the PWM output, it toggles at the rate of FOSC. The advantage of PWM is that it has a much lower toggling rate with the fewer transition during any given period of time. This helps reduce the impact of the switching errors and the dynamic power. For PWM, the two popular modulation schemes are AD and BD modulation. When deciding on architectures of Class D amplifier, it involves the selection of the modulation scheme and the topology for the modulation scheme, and it includes PWM and PDAM. And the PDM has a high pulse rate while PWM has the low pulse rate, good performance and low power consumption. So PWM is a clever winner. Deciding on the digital topology versus analog feedback topology involves the trade-off between performance and power consumption. Digital implementation has a lower power consumption and a lower performance, while analog feedback provides good performance at the cost of power. And depending on the system of the requirement, it can be PWM Class D amplifier with digital or analog feedback implementation. Digital PWM Class D, digital triangle waveform with an oscillation frequency of 667 kilohertz is compared to the output of the digital loop filter. The digital is clocked at the 24 megahertz, and the output of the digital comparator is a PWM signal toggling at the rate of 667 kilohertz. This PWM signal is the feedback within the digital feedback loop of the modulator. Timing distortion errors in the PWM signal due to the uniform sampling of the comparator are reduced with the high forward loop gain in the digital feedback loop. Figure 13 shows the digital PWM Class D amplifier which has digital input and a digital loop filter and a switching driver. The target dynamic range is 120 decibels. The digital PWM modulator should be carefully designed, and the analog noise from clock jitter supplies should be analyzed and modeled. And of course, digital implementation can offer low current and consumption, and there is no need of analog DAC. digital analog converter. Increasing the modulator order beyond the fourth order does not significantly enhance the quantization noise performance, but rather decreases the maximum input range for the modulator is stable. Increasing the range ratio of fs by FOSE improves the pulse width resolution, with thus reduces the noise. However, the modulator consumes more dynamic power with a higher Fs, and the lower limit of the switching rate FOSE is restricted by the unity gain modulation frequency of the output transfer function. Here, figure 14 shows a digital PWM modulator. Analog feedback implementation. The feedback loop helps to reduce the distortion and noise and improve the power supply rejection. Higher power supply ratio, rejection ratio, PSRR at 217 Hz is critical in a global system for implement mobile communication GSM system. The Class D amplifier produces pulse width modulator outputs with fast transition and rail-to-rail swing. Conventional architecture directly feedbacks the Class D output to the input of the low filter, causing the large common mode CM variations and a large disturbance at the input of the loop filter. Consequently, the Class D amplifier performance is limited. The loop filter output includes a large signal swing when the input signal is here. This is not only increases the current consumption of the amplifier to support the large output swing, but also limits the error correction range before the loop is saturated. For the loop to efficiently compress the battery disturbance in the mobile system, the signal level, namely the output power, has to be limited to keep below distortion. An effective EMI reduction approach with the detailed implementation of the half H bridge and a pre-dive circuit, the output switching edge rate is controlled by the power switch gate voltage, and the switch gate voltage is provided by the pre-dive, which consists of the chain degenerated digital gates. The auxiliary path enables the loop of the settle without affecting the output voltage across the speaker. During power up, the strength of the power driver gradually increases until it reaches its maximum, and while the strength of the auxiliary driver gradually reduces to zero. Enhanced analog feedback Class D architecture shown in the figure 23 resolves all of the issues, and it includes a feed forward and analog to digital converter, ADC path, and feedback filters and edge rate control in the driver stage. The feed forward path is designed to process the signal during the loop filter to integrate only the difference between the input and feedback signals. The loop filter therefore mainly responds to errors injected into the loop. This architecture is significantly extends the loop filter operation, and the loop filter operation therefore mainly responds to the errors injected into the loop. This architecture significantly extends the loop filter operation range to support a much larger signal and level, and thus large output power capability. To avoid PSRR performance degradation due to the feed-forward architecture, the loop filter feedback and the feed-forward paths are powered from an internal low dropout regulator. The feed-forward path basically provides a period modulated RAM signal for PWM generation. This is very different from the conventional PWM generation with the period fixed RAM signal. Conclusion. In summary, compared to the other amplifier classes such as A, B, G, and H, and so on, Class D has a superior efficiency, and audio Class D amplifier can be realized during the digital PWM architecture and analog feedback PWM architecture. An enhanced analog feedback PWM Class D amplifier with a wide point package achieves 95% of peak efficiency and a 105 decibel dynamic range. The feed-forward ADC path and the edge rate control enables a high output power and a high margin for EMC. The feedback filtered path enables the 0.004% minimum TD and THD plus N performance, and the fourth order loop filter helps to achieve 96 decibel PSRR. Um, 1 MV pop click is achieved with the auxiliary loop and ramp up down and techniques. Thank you.